Goings in. Let it out. That's okay. I do it like this.
Okay, so you count 4, 5, and 6, right? You count 1, 2.
Total. 4's in there, 5's in there, 6's in there, 7's in there.
Oh, that's all you have to say?
Well, how many though? How many 4's, 5's, 6's, 7's total? Everything that's in there, count them up. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 out of how many? And what percentage? So each divided by 12. I did? Okay. Alright guys, so I gave all my copies away. I had exactly the right number except for me. So I'm going to keep this up here. So what did you guys get for, so this sum should have been what? That's in the second column, right? 0. Cool. Unless you rounded the mean, and then it wouldn't be 0. Don't round the mean. And then this, what did you get for the sum of that squared? 68.25. Good. Sounds right. And then to do the formula, the sum, now this, I really want to make this clear. Let me be clear. You don't plug stuff in here. That doesn't make a damn bit of sense. This says, get a whole bunch of those. We did. And then add them up. We did. So this whole thing is 68.25. That is what the sum of these are. And let that really sink in. That part is the part that you're not used to from algebra, replacing an entire thing with a number. But that's what we figured out. This whole thing is that. And then n minus 1 is... How many people are there?
Oh, sorry.
12.
Oh, sorry.
12 minus 1, 11.
I said the other.
And then that is... Blah, blah, blah. And then when you take the square root, that's your standard deviation. What's the square root of that?
491.
491? How people do. I think most everybody I saw got that. If you didn't quite get that, see where you went wrong. Did everybody get that? If not, you know where to look to see where something went wrong. And then did you put the right thing there? It's n minus 1. So it should be 12 minus 1, 11. Blah, blah, blah. That's my standard deviation. Now, what do I ask you to do with that? I forget. The first thing I say... Oh, yeah, good. All right. Hey, guys. Side note. If my mean was 50 and my standard deviation was 10, how many standard deviations away from the mean? How many standard deviations from the mean is the data point 60? 1. Okay, good. Let that be easy. How many steps do I call them steps because that's exactly what we do. We step around the data using the standard deviation. So how many steps from this is 60? It's 1 step. If every step I take is 10 big, maybe 10 inches. It's 10 inches big, and I'm at 50 inches, now I'm at 60. How are we doing? So that's 1 step it took to get there. Alright, so that was easy. You can just see that without doing any math. Well, how many standard the mean is 63.72. Exactly. Don't estimate. I want to know exactly how many steps it is.
4.3?
No. Yeah, well, how would you do it though? Let me make it more interesting. Let me make the standard deviation 10. I forgot. It's too easy. Let me make that 11. Right? So what would 63.72 be then? How would I figure out how many steps fit into that? Well, first I have to figure out how far is it from 50, period. Right? How far is that away from 50? Well, it's 63.72 minus 50. Let me let that sink in. And then I want to see how many steps fit into that. I want to see how many steps fit into that distance. So I want to divide by 11 to see how many of these fit into there. Isn't that x minus x bar divided by s? That's the formula I gave you. So what does that formula represent? The number of standard deviations from the mean to the data point. That's what it represents. And some of you guys might know that's called the z-score. The z-score. Now, I really want this to make sense. Standard deviation, if my data is really spread out, what does my standard deviation do? Does it get bigger or smaller? It gets bigger. So then I can step around it, right? So if my cities are really far apart, what am I going to use to measure the cities? Am I going to use millimeters to measure how far the cities are apart? Well, that's dumb. I'm going to use kilometers, or, we're in America, one of only 3 countries on the face of the earth that doesn't use metric. We'll use miles, maybe. Right? Do you guys know that our system is based on how big the King of England's foot was?
Yep.
You guys know that? Where the hell's the revolution? We're like, come on, didn't we have the whole freaking original Tea Party, not the current Tea Party bullshit, but where we dumped it? All right, sorry, this is not history class. Standard deviation is like the tick mark on my ruler. If it's towns, I want to use miles. If it's how far apart people are in a classroom, I want to use inches, right? Unfortunately for us. So this is like the tick marks on the ruler. This is when I lay the ruler down to see how far apart things are. How many standard deviations is this? It is, what did you get? What was this? Somebody do this for me? 1.247? Am I hearing you right?
Yes.
Alright. So that is that far away from the mean relatively. It's like a little more than a step away. So that gives me an idea that how relatively far. If I got to like 3 steps away, that's really damn far. So if your z-score for height was 3, that means you're freaking tall as hell. You probably have to duck going through that door because you're really above the mean. Do you guys get the idea? A little bit. Obviously, we're going to do a lot more with this. They don't even call this a z-score yet in chapter 2, which kind of irks me a little bit. So if you didn't quite get everything I just said, it's all going to come back at you again eventually. All right. So for the problem you got, what did I say? I said, how many standard deviations away is it to 9, right?
Yeah.
So 9 is the value that I want to look at. So that's x. X bar is 6.25 for this data always, for this data. So then the z-score will be x minus x bar divided by standard deviation. And just to reiterate, why did I do this? Because standard deviation, you always take it out at least 3 places. That's huge. At least take it out 3 places. And what do you guys get when you do this?
1.104.
1.104? Does that sound right? Is that what you guys got? Okay. Sure, I like that. Sure, I got that. I wasn't right? Sure, I didn't get that. All right. What was the next? Oh yeah, so the last piece. Eventually we're going to talk about normal curves. Has that escaped my mouth yet? Normal curves?
Yeah.
That's the same as a bell curve, right?
Yeah.
And normally you think about bell curves in relation to like IQ scores and stuff like that. Have you guys, or the bell, when curve grades, we use the curve and then we pick it up and move it. That's how you curve grades. Oh man, the highest grade was a 60. Now the highest grade is 100 and you see where everybody else fell. You guys realize that's how you curve grades? It's not exactly how I curve grades. I kind of changed the standard deviation at the same time. Because I'm in the stats teacher. But, let me think. What was I getting into? Oh yeah. So we're going to eventually talk about bell curves. And what's interesting is if I go 1 step out from the mean, I will always catch about 68% of the data. So if I knew the average male height, and heights of men are normally distributed, I would know 68% of the men are 1 standard deviation down and 1 standard deviation up from the mean. I would just know that. And why did they make the door that high? Because they could then tell, well, how many men are taller than that? And I only want a certain percentage of men to have to duck, so I know how tall to make my door, right? If we were all hobbitses, the doors would obviously be shorter and maybe wider, right? To accommodate our girth. on our big sticky hairy feet. Oh, sorry. I don't know what the feet have to do with the width of the door, but well. Okay. So your problem was put the mean in the middle. What was the mean? I forgot already. 6.125. Go up one step and down one step. So if you go up 2.491, where do you end up? 8.741 in stereo. And if you go down one of these, 3.759. All right. What data points do you catch? If this is like a net that I'm throwing out, what data points do I catch in there? There's 3 in there. No, it's back here, right? What's in here? 4, 5, 6, 7, 8, but there's no 8s, right? So how many data points? Don't tell me 4, because there's more than one 4, there's more than one 5. How many total data points did we catch in the net we just cast out? 8 out of how many total? 12. So what percentage did we get within one step of the mean? 67%, roughly. 66.66. Okay. Which is really close to 68%. So I mean, it doesn't. You guys don't realize what that means yet entirely. If you look at the, if you look at your data, that's not there yet. You have to take a look and see if it's actually bell-shaped. There are other ways to have this percentage of the data in there. Stay with me now. All right. But this is a question that I ask on several of the first tests, so a couple of the first tests, maybe the first 2 tests, I should say. I love this question because we're going to look at this question in a few different ways. Why do I love this question? Because we have so many theories and statistics about what percentage of the data is in here, is in there, is in there. So I like a problem where it's concrete, not theoretical. You can actually just go count the damn things. How many are in there, damn it? Don't tell me theoretically. You can actually go see. Oh, 8 would be in there, but there are no 8s in the data. Yeah, I would count any 8s I see, but there are no 8s in the data, right? Oh! How many total data points did we catch? There were 2 4s, right? And
2 4, 2 5, 2 6.
and so there were a total of 8 things I caught. I like it. What time is it? Oh, that's good. Hey, it's all right. Sucker guy. You guys good? You guys, is that enough? You guys want to do more? I can always do more. Well, no, not really. I think that's plenty. So next time, I'll have the answer key for the practice test. I'll have the quizzes graded. The test is on Wednesday. Okay. A week from today.